Okay, let's start. Okay, so let us start the first problem, which is this one. Okay, so what you are given is a vector field, and the question is this vector field irrotational? So in vector analysis, so what is vector analysis? Maybe that's the first thing you can ask. So vector analysis is basically calculus, but the objects on which you do calculus are no longer functions. Okay. So what is basically calculus, right? If I had to give you like a very bird's eye view. So calculus is basically um, is basically having a quantity and then asking how this quantity changes across the domain of definition of that quantity. So the first thing that you can think of is a function. A function is the most basic mathematical quantity, and and differential calculus is basically studying how a function changes across the domain of definition of the function with respect to small changes. Okay. However, you are not restricted that the quantity which you want to study or whose change you want to study has to be necessarily a function. In fact, there can be various kinds of mathematical quantities on various kinds of mathematically defined domains where you can do analysis or calculus. So today we are essentially interested uh, in vectors. Okay. So of course, if you were to ask me um, what other quantities are there for which we can do for which we can define a notion of calculus, I would say it would include, yeah, I would say it would include functions, it would include vectors, it would include tensors, and in general, you there are in general you could define sections of certain bundles on which you can do analysis. So so our interest fields of interest are uh, functions basically and vector fields. So the question is, what is a vector field? So what is a first of all, let us ask what is a function. So a function is so that well, I mean, when you say a function is basically a map, right, from f to, let's say, r. Okay, um, or some rk. Where this u is generally some open set of some rn, right? So okay, so a function is, I mean, this is all very very basic stuff, but a function is basically a rule which to each point of u associates, let us for the time being assume that this is r only, not rk. So function is a rule which at each point of u associates a scalar value to it. Okay. So a function is basically what we called a scalar field. So whenever you see the term field appearing, of course there is a notion of what we called a field in the area of algebra, which is a field is a specific algebraic object which has algebraic properties. But here we're not dealing with that kind of field. So whenever you hear the term field here in the context of analysis, a field is what you should think of a field is that a field is a function. It is sort of a function or a mapping. What it does is that to each point in the domain, it associates a quantity. So a scalar field is something which at each point of this domain U, it associates a scalar value. So you can write this rule as this. So if U is a point in my domain U, this function, what it does is that to each point U, it associates a scalar value, which is f of U. Okay. So I hope this is clear. So if you were to ask me, like, give me a practical example of what is a field, you can think of, let's say, pressure in the room. If you are in a room, just think of the air pressure that is there in the room. At each point in the room, there is this physical quantity, which is the pressure, which you can measure. So so the pressure is an example of a scalar field. Okay. Now, just like scalar fields, you could also have a field which associates to the point U, not just a scalar, not necessarily a scalar value, but some other quantity, say a vector. Okay. So a vector field, so I'm just going to write down a small definition here. If you know all this stuff, then I can skip directly to the problems. Otherwise, I can maybe like give a brief intro. So a vector field, what it does is that it associates to each point a vector. Okay. So if we continue with the analogy of air pressure, now you can say something like, what is the uh, what is the air velocity at that particular point? So the air velocity at that particular point in your room is a vector, and air velocity in general is a vector field because uh, different points in the room will have different values of the velocity vector of the air. So you can think of it as a map V from some domain U to essentially vectors. So you can sort of think of it as like RK. Where, of course, this U is a subset of the space RK. Okay. So it's not just any arbitrary mapping. It's a mapping which associates uh, to uh, to a subset U of RK, a particular vector. Okay. So this is an example of a vector field. Now, of course, when you do calculus on functions, you can take derivatives, right? So we saw last time we looked at this operator, nabla operator, and this nabla operator operates on functions. So from now on, I can interchangeably use the term function for a scalar field. Okay, it's kind of nice to sometimes think of functions as scalar fields. They're just one and the same. There's no difference, but it kind of when you think of a field, you can think of some physical quantities like pressure, temperature, etc. So this grad of f is a um, is an operator, and you can think of it in this way. So this grad is a map which which what it does is that it takes a um, if I'm being like really very strict about it. So what it does is that it'll take a C1 function in U, and it'll essentially give you a continuous function. So it will take a function f, and it will basically give you another function which is called grad of f. Um, but it's not a function necessarily. It'll actually give you a vector field. Okay. So this is not a map from C1U to C0U. In fact, this is actually a map from C1U to the set of vector fields over U. So the set of vector fields over U, there are various ways to sort of denote uh, the set of vector fields over U. I'm going to use this symbol. Okay. So I'm going to use the symbol. So I'm going to essentially use I'm going to use this symbol gamma of U RK as the um, as the set of vector fields over U. Of course, when I say the set of vector fields over U, one has to then say if this is continuously defined, if this is smoothly defined, how it is defined. So just for the sake of just so that there isn't like too many symbols we're using here, just let's assume that the function is a smooth function. So then we can think of this nabla, this grad, as an operator which operates on functions and gives you vector fields. Okay, so this is the set of smooth vector fields. Okay, where this U is an open subset of RK. Okay, so this grad is basically like an operator which takes a function as an input and basically gives you a vector field. So let's take an example. The best example that you can probably think of is um, is um, right. So maybe you can think of this. So you can think of, let's say, an energy potential function, and let's say so say phi is the electric potential then this grad of phi, actually it's actually minus of grad of phi because of sign reasons. This is E is the electric field at that point. Okay. And what is this grad? So we saw this grad last time. So grad of f is basically equal to it is this vector which is del f upon del x1 all the way to del f upon del xk. Okay, so this is grad of f. So this operator grad, which is basically a differential operator, is acts on functions and gives you vectors. Okay. But when you're in the language of, when you're in the context of vector fields, there are, well, of course, uh, you can ask how a vector field changes from one place to another place. And that, of course, leads us to the definition of what we call a connection. But we're not going to go there. Instead, we're going to look at how this nabla operator is defined on vector fields in general. So, in the context of vector fields, uh, so if you were to sort of think of this operator, you can think of this operator grad as essentially equal to um, del x1 multiplied with the unit vector e1 all the way to del xk multiplied with the unit vector ek. So then if you do grad of f, which is sort of like a vector multiplied with the function f, then you will get this particular vector. Okay. So we take this nabla as a differential operator, and we can operate this on vector quantities. Okay, I'm not sure how the mic um, got muted, but anyway, that happened. Okay. Right. So this basically turns out to be equal to um, del one x1 uh, e1 cross e2 plus sorry, it's actually del one x2. Sorry, del one x2 plus del two x1 um, e2 cross e. Let's look at this problem. We have seen this kind of problem before. So find the unit normal to this particular surface. So we discussed at length last time about surfaces which are given by these the inverse values of functions, right? So we talked about if you have a function f from R3 to R, and we discussed the conditions under the regular value theorem when f inverse of 0 is a surface. Okay, so in particular, it will be a surface if and only if 0 is a regular value. Okay, and we also saw last time that if you have a function f for which f inverse of 0 is a surface, so then if you compute the gradient of the function at that particular point, then the gradient will always be normal to the surface. So grad of f, so say s is equal to f inverse of 0 is a surface, then grad of f is normal to s. So what do you mean by normal to s? So it means that if you take any vector v, which is what this means is that for any point p in S and for any vector v which is in the tangent plane at this particular point S. So I'm going to draw a picture over here. So let's say this is your surface, and let's say this is a point over here. So here at this point, you can have a tangent plane at this point. And so let's say this is your point P, and you have a vector v in this tangent plane. So for all points P in S and for all vectors v in the tangent plane of S, this grad of f at the particular point P is going to be normal to v, which means that if you take the dot product or the inner product, this is equal to 0. Okay. So grad of f is always normal to the surface. It is a unit normal if it is also a unit vector. Okay. So to get the unit vector at a particular point P, let's say it is NP, you can do grad of f by norm of grad of f. Okay. Uh, right. So essentially, what is grad of f? So grad of f is equal to del 1 f, del 2 f, and del 3 f. What is that equal to? So del 1 f is equal to y cube z squared. Del 2 f is equal to 3x y squared z squared, and del 3 f is equal to 2x y cube z. Okay. Now substitute the values of del f at -1, -1, 2. You will get at this particular point, which is this point, we'll get it as equal to -4, -12, and 4. Just writing the vector as as this triple, and then of course you can then compute the unit normal in the surface. Okay, if you have any questions, feel free to ask me. All right, let's proceed. Okay, so before proceeding, let me just um, state one result. So you are given a vector field. Um, so and it is said that this vector field is irrotational. Okay, which means that the vector field is um, is actually the curl of that vector field is equal to 0. So I'll just tell you quickly. So if a vector field is irrotational, which means that the curl of that vector field is 0, then in the language of physics, we call those vector fields as conservative vector fields. Okay. So examples of conservative vector fields are, let's say, um, a conservative force. Okay, a conservative force. If you think of a force like gravity, electricity, etc., these are conservative forces. Okay, so conservative force is a force where you might have you might have known this from high school physics only. So conservative force is that if you move along a closed path, then the work that you do as a result of that force is basically equal to 0. Okay, so but that is the definition of a conservative force. Um, but here, I'm calling a conservative force as a force in which the curl of that force is equal to 0. Now, of course, you might ask that the two definitions seem to be different, but they're not. So there is this theorem which is called these Green's theorem or the Stokes-like theorems, where you essentially connect the curl with an integral. I'll show that later on when the appropriate problem comes. But so if a force or if a vector field is irrotational, so you're given a vector field which is irrotational, which means that curl of f is equal to 0. So if curl of f is identically equal to 0, not at a particular point, it's identically equal to 0. So then, this is the theorem we just stated. There exists a scalar field phi such that grad of phi is equal to f. Okay. So in other words, what this means is that I can, if you give me a vector field for which this curl of f is equal to 0, then that means that I can realize this vector field as a gradient of some scalar field. Okay. And so some of the consequences of this theorem, which you might recall from physics, is that um, just think of something like the gravitational potential, right? So if you take the gravity field, then the gravity field is an irrotational field. So the curl of that is 0. Uh, as a result, you can define something called a gravitational potential. Similarly, if you take the electric field, then the electric field also is an irrotational field. The curl of F is basically equal to 0. And as a result, um, yeah, and as a result, you have the electric potential. So, what is the electric potential? The electric potential, as we discussed, is a field, is a scalar field phi, for which this gradient of that scalar field is basically equal to that corresponding force field. So this is in general a theorem. Which the theorem is that if a if a if a vector field is satisfies this property that curl of f is equal to 0, um, then that vector field necessarily comes from a scalar field. Okay. Now I just want to point out one caveat that this is true. This is not in general true uh, uh, for all surfaces. Okay. This is true for, let me just write it down over here for R2, R3, etc. This, let me just put a note over here. This is not necessarily true for all surfaces. Okay. And the reason why it's not true for all surfaces is it's a very deep reason. It's related to the topology of the surface, which I will not be able to discuss. But essentially, uh, essentially, the first de Rham cohomology of the surfaces, or the manifold in general is 0, then you can say that every vector field that satisfies this property, that curl of f is equal to 0, must necessarily come from a uh, must necessarily come from a scalar field. Okay, we must necessarily have a scalar potential backing that field. Not all vector fields can have scalar potentials backing that field. Okay, but this result is true for R2, R3, but it's not necessarily true for all surfaces. There is a particular topological obstruction to uh, to which tells you when this theorem holds or does not hold for complicated surfaces, and it's a cohomological uh, it's a basically a cohomological property. Okay, so but here there is nothing mentioned, so you can assume without any loss of generality that this vector field f is is defined for R3. Okay, it's defined all over R3, and so this result holds. So now you have this vector field f. It's given to be curl free. So curl of f is 0. What you need to compute is you need to compute a phi such that grad of phi is equal to f. So let's see how this can be done. Okay, just give me 1 second. Okay. All right. Okay, just give me a moment to think. Okay, so what you need to do is so let us say phi is my corresponding scalar potential. What I want is I have del phi upon del x equal to f1, del phi upon del y equal to f2, and del phi upon del z equal to f3. Okay. Now, of course, you are not given appropriate boundary conditions. So, if you want to solve for, so you have a system of first order linear partial differential equations which you can solve. So, for instance, if you solve the first one, you will get phi as equal to as basically integral of f1 dx, plus you must add a function. Let's call that function lambda, and lambda is a function of y comma z. Okay, so lambda is a function that you don't really know what that is. So let us actually solve this. So this is equal to integral y squared cos x plus z cube dx plus this lambda y comma z. Okay, so if you just solve it, then you get this to be equal to um, you get y squared sine of x plus z cube x plus lambda of y comma z. Of course, you have to determine what this function lambda is, um, right? So what you can do is you can now take partial derivatives. So you have phi over here. So if you take del phi upon del y, you get 2y sine x. This is 0 plus del lambda upon del y, which you can equate to f2. F2 is 2y sine x minus 4. So of course 2y sine x gets cancelled and you get del lambda upon del y to be equal to minus 4. Okay, so let's continue. So if you write, so you can solve for this lambda, and lambda is equal to minus 4y plus some function of z. So let's call that lambda 1 of z. Okay. But lambda 1 of z has to be determined. So now you do del phi upon del z. So del phi upon del z is, again, this is equal to 3z squared x plus del lambda upon del z, right? This is equal to 3z squared x plus lambda 1 dash z. Okay. This you have to equate with f3. F3 is equal to 3xz squared. Okay. So what you get is that lambda 1 dash of z is equal to 0. Therefore, lambda 1 is basically a constant, is some constant. I'm just going to call it lambda 1 only. And so if you just plug that in, I think you get y squared sine x plus xz cube minus 4y plus c. This is the right answer. Okay. So I hope it's clear how we proceeded with the problem. If you have any questions, I can pause for a minute. Okay, I can pause for a minute or two. If you have any questions, I can wait.
Excuse me, sir.
Yeah.
So I have this question that
Yeah.
how do we
Please.
relate this concept of fields in maths
Um,
to the concept of gravitational fields in physics? I'm unable to understand that.
okay. Okay.
Mhm.
If I may ask, like, Are you a undergrad student?
Yes, sir.
Okay. Okay, sure. You are in engineering or in any science field, if I may ask?
Sciences, sir.
In sciences?
Mhm.
Okay, okay, sure. So, okay, so your question was, how do you relate the concept of field to the concept of force fields in physics, let's say, or potentials, let's say. So, okay, so when you hear of, so just to give you like a small history, um, this kind of mathematics actually came from physics. It was not that the math was invented first and then applied to physics. These were physical phenomena which inspired the development of the mathematics. So when you talk about, hence the term field, because physicists have been using the term field uh, for a very long time in this context. So so just think of an electric field, right? So the electric field uh, is is a conservative vector field. Okay, by that it means that um, if you if you give me a um, like a closed loop, okay, if you give me a closed loop, and um, if you sort of uh, do work against this closed loop. So in other words, let's say to give you an example, let's say there is some electric field out there. Okay. And that electric field is, let's say there is some charge or a set of charges, etc., which is producing this electric field. Now, if you, of course, now if you place any other charge there, whether it's a positive charge or a negative charge, it will experience that field, right? And you have you have the equation, uh, which is the uh, which is the force that it will be facing. Now, now, if you were to take this charge and move it along a closed loop, then the work that will be done by you is actually going to be equal to zero. Okay, and uh, physicists knew this for a very long time, and the reason or because this is the case, because for an electric field, if you do this, if you move along a closed uh, path, uh, the work done becomes equal to zero. The electric field can be expressed as a potential. Okay, which is the reason why you have an electric field potential or a gravitational field potential, but you do not necessarily have a magnetic potential. Okay, I mean, I understand there is some concept of magnetic potential in electrodynamics. I can't recall the physics at this point, but but the reason is that the magnetic field is uh, is not actually uh, is not a conservative field. Okay, so fields have to be conservative. Conservative means that it has to be rotational. So let me just write it over here. Conservative conservative field means that the curl is zero. So I'll just write it as curl free. Which means the curl is equal to zero. And then that implies that there is an existence of a potential. So if you recall, just give me 1 second. So let me just bring this up. Maybe you have seen this. So okay. So these are the Maxwell's laws of electrodynamics. Okay. So you would see over here that the curl of E is equal to the rate of change of the uh, magnetic field, right? And now if there is no magnetic field around, then E becomes a uh, conservative field, and you can then define the so-called electrostatic potential. Okay. Um, and of course, you have these two quantities as well. So the first quantity is basically called the divergence of E. Now, if I were to give you um, a physical meaning of what this divergence of E is, so the divergence of E is basically is yeah. So essentially, what the divergence of E is that if you give me an infinitesimally small closed surface, okay, um, just give me 1 second. Uh-huh. Okay. Yeah. So what this divergence is that if you give me an infinitesimally small closed surface, okay, and you compute how much uh, how much electric flux comes out of that surface, okay. The amount of electric flux that comes out of that closed surface, this has to be a closed surface, is basically given by so let's say E is the um, so let's say E is the electric field at a particular point. So then it's given by E dot N over the surface ds. Okay, N is the unit normal vector. Now, now if this surface was very tiny, if you took like an infinitesimally small surface, then then the divergence of E is basically uh, the amount of flux that is coming out of this tiny closed surface. Okay, and um, and so essentially what this first law of this electrodynamics is stating is that the divergence of E uh, uh, is basically equal to the rho, where rho I think is a charge distribution. So if you take like an infinitesimally small surface which is enclosing a charge whose density is rho at that point, then that is basically the divergence. So it's a measure of flux. So essentially what you're doing is that you have, let's say, the electric field at various points of the surface. So to give you like an example, let's say you have a closed sphere. Let's say you have a closed sphere, and let's say you place a charge Q somewhere. So then at each point, at least by Coulomb's law, you have an electric field, and that electric field would be directed from the charge um, to uh, the point at that particular place. Um, And so let's say if you were to take this electric field, which is now defined on the surface, so each point of this sphere has this electric field which is induced by the charge, and uh, if you were to basically compute um, if you were to basically compute the whole flux that comes out of the of that um, of that surface, then that would be equal to the charge enclosed by the sphere. So this is, of course, you have like a single point charge enclosed at it. But if you had like a if you have like a charge density which is spread all over the volume of the sphere, then the divergence of E would capture like a infinitesimally small amount of flux that would come across, that would come out of a tiny volume. So if you chose a tiny volume over here, and if you just drew like a surface that bounded that tiny volume, then the amount of electric flux that comes out of it would be basically given by the divergence of it. Okay. So it's basically a differential quantity. Um, so does this make sense a little bit?
Yes, sir, somewhat. And I
Yeah.
believe that
Mm.
is it from this reason only we say that the curl is zero for irrotational vectors, that it could be expressed in the form of a scalar potential.
Mm,
Because the curl of any, like
uh-huh.
for curl, like the del cross of del phi would be zero eventually.
Right, right. So
That's how
yes,
we arrive here, or we define that irrotational vectors, for them the curl is zero. That's why there's an existence of potential.
so the reason why the curl why curl free is called irrotational is basically this. So there is this theorem which is called, I think it's called Green's theorem. Keep on forgetting which is Green's and which is Stokes, but um, so these are, so essentially the theorems are identical only at a sufficient level of abstraction, but you don't need to worry about that. Which is, if you give me a closed curve, so let's say you are in R2, simple, and you have a closed curve. Okay, so let's say C is a closed curve, and you take you have a vector field, let's say F is my vector field, and you essentially move along this closed curve. Okay, so you compute the work done by this vector field uh, along along this uh, closed curve. So you write it like this. You write uh, this is your curve C, this is C, and you write F dot ds. Okay, so F dot ds is basically the total amount of work that you do when you traverse this closed curve. So in traditional physics literature, sometimes we put like a bubble that shows that this is a closed curve. Okay, this is like old notation. In modern day mathematics, we do not use these kinds of notation, but they're still used from physics. So this theorem basically tells you that this quantity is equal to the curl of F, the curl of F, and if you take the area of this particular uh, so this curve C bounds a particular area, right? Um, so if you take the infinitesimal sort of area element, then this is equal to curl of F dot dA. Okay, where dA is the infinitesimal area element. It's kind of best understood in this way. Assume this was not a R2. Assume you had like a surface. Okay, let's say you have a surface which is sitting in R3. And you have, let's say, a closed curve, okay, which is C, and you have this force field as usual. So now if you compute the work for this particular closed curve, which I'm going to write as integral F ds for this closed curve C, then that would be, so there is a particular subset of the surface which is a closed area, which is a closed region, which is covered by this surface. So basically what I say is that U is a bounded region of the surface of S, let's say this is my surface, such that the boundary of U, so sometimes we denote the boundary of U as U dot. Okay. So the boundary of U is this curve C. So then this is equal to integral of curl of F. Okay. And then you can take an area element. Okay. So the area element in this case is it's a bit tricky how to define it. You can still define it, but let's just say you have some area element. So the area element is going to be like a tiny area like this, which with a unit vector along this direction. So notice that curl of F would also be pointing normally. Okay, so it would be pointing in the same direction as this normal vector. So this is equal to dA n cap. So dA is the area element n cap. So now what happens is that if the curl is 0, then the work that you have done is actually equal to 0 for moving across this, for moving along this closed closed loop. Now, what this means is that this is not a rigorous statement, but what this intuitively means is that if the curl of F at a particular point is equal to 0, maybe it's not identically equal to 0, but at a particular point it is equal to 0, then what this means is that if I draw a tiny loop around that particular point, let's say this is a point P, and let's say curl of F at P is 0. So it's not identically equal to 0, but it's only 0 at P. So what this means is that if I draw if I draw a tiny loop around this particular point P, and if I compute the work done for this field F for this tiny loop around this particular point P, then it would be equal to 0, or the limit would be equal to 0 as you shrunk that curve to P. Okay. And so what this curl is capturing is that it is capturing in some sense the amount of rotation that you have around a particular point. Okay. And hence if something is curl free, you call it irrotational. Okay. And the thing is that there are many quantities in physics which actually are derived from curls, which are basically curls of certain vector fields. So, for instance, the vorticity vector in fluid mechanics has in it the definition of a curl. Next, you have, I think you have one of these forces, the so-called can't remember right now. Well, I can't remember right now. So you have these quantities which actually measure how much a vector is kind of. I don't want to use the term this. How much a vector field is in some sense curling around itself. Okay. If it's not curling around itself, then essentially what means is that for a tiny loop, it's going to be equal to 0. Curl is also, I think if you are building these transformers, then in electrical engineering, I'm not from an electrical engineering background, but in electrical engineering, when you're building these transformers, then you have these eddy currents that show up in a transformer. And these eddy currents actually lead to a lot of loss of energy or loss of power in the transformer. And I think you define the eddy current also as a curl. Okay. So yeah, I mean it's got to do something with rotations. That's why That's why the term is there.
Understood,
Okay.
sir. Thank you.
Yeah, let's proceed. Just give me 1 minute. Mm, okay. Not seeing many interesting questions. Okay, so let us. I think this problem is okay. It illustrates a point. So let's. Okay, so for a given vector field, there is a very there is a very natural concept which is called the flow lines of that vector field, right? So maybe you have seen um, these in physics where uh, uh, you can sort of draw these electric field lines. Okay, the electric field lines is basically how the electric field um, um, is uh, is at a particular um, um, okay, just give me 1 second. Okay. Well, okay. So let me just write down one concept over here. So it's called the flow lines of a vector field. Okay. So what does this mean? So when you hear the term vector field, the way you should sort of picture it is that at each point you have a vector. So let's say you want to uh, picture a vector field in this way. Like think of a domain like this, and you have at each point some vector. Okay. It's not necessary that the vectors always point in the same direction or are same. You have a think of vector field in this way. Okay. Now, so the flow lines is that if you start off from a particular point P, you can follow. So the vector field basically gives you a direction, right? At each point you have a vector. So you can follow the vector which is at that particular point, and you can move along that particular field, right? So what this will do is this will basically trace out a curve. Okay. Um, and so this curve is called the flow line or the integral curve of the vector field. So let me just write it over here. A definition. A flow line slash integral curve of a vector field. Okay. So what this is that you start off from a point P. This is, let's say, your initial point, and um, you follow the vector field. So let's say X is my vector field. You follow the vector field X, and then as you move along, you again follow the vector field in that direction and so on. So this will trace out a curve. Okay. So the definition is that phi P comma T. Okay, let us not write it this way. Let's just say phi P T is the integral curve for X. So X is my vector field. I'm always denoting vector fields by capital letters, X, V, and so on. If phi dash T is equal to X of phi of T. So what does this mean? It means that, so this is your curve, and phi dash T is basically the tangent vector to that curve. So what you're saying is that the tangent vector to the curve is basically equal to the value of the vector field at that particular point. Okay. Um, let's just give you like a very simple example. So let's say you start off with a vector field, which is, let's say it's given by x1, uh, x1 e1, x2 e2 plus x3 e3. Okay. So let's say all these xi's are some functions of x, y, and z. Okay. So then an integral curve would be a curve which satisfies this relation that phi dash t. Okay, maybe not phi dash t. Maybe just you write the integral curve phi as, so phi has, let's say, three components. Let's say phi 1, phi 2, phi 3. Each of these components are functions of time. So basically each phi I is a function of time. So then what this means is that phi dash t is equal to x of phi of t. If you were to write this down in the form of components, what this means is that phi 1 dash of t is equal to x1 of xyz, but the x coordinate is phi 1, the y coordinate is phi 2, and the z coordinate is phi 3. Okay. Similarly, you get phi 2 dash of t is equal to x2 of phi 1, phi 2, phi 3, and phi 3 dash of t is equal to x3, phi 1, phi 2, phi 3. Okay. So what you have is that you have a system of uh, of first order. Uh, it's a system of first order uh, ordinary differential equations (ODEs), and um, and basically you can always find a solution locally. Okay. In fact, you can always find a solution for all time, because you're going to just assume trivially that X is a vector field on R3 or R2, whatever. So unless stated otherwise, we're going to always assume that the domain in which these vector fields are defined are R3 and R2 and so on. So you have a system of first order ODEs. These are not necessarily linear ODEs, because like, for instance, let's say your vector field is something like this. So let's say your vector field is x squared, is x squared, y squared, z squared, and z squared x squared. So then the terms over here would look very odd. So you get uh, you get basically phi 1 dot is equal to phi 1 squared, phi 2 squared. Phi 2 dot is equal to phi 2 squared, phi 3 squared. And phi 3 dot is equal to phi 3 squared, phi 1 squared. So it's not necessarily going to be like a linear ODE, but you will still get a system of ODEs, and you can solve for these system of ODEs to get a curve. Okay. But in order to solve for the system of ODEs, you need an initial condition. So the initial condition is basically this. You will set phi 0 at P. So this is the initial point. So you start off from a particular point P, and then you start to trace out a curve. Okay. At each point in the curve, the tangent vector to that curve. So if you call this curve as phi, then the tangent vector to this curve, which is phi dash of t at this particular point, is basically equal to the vector field at this point. Okay, so this is the definition of an integral curve. And I'm just going to state like a few facts. So so what this phi is doing is that this phi, you can think of it in this way. So phi has two parameters in it. Okay. So one is the time parameter, which is, of course, it is defining the curve. And the second parameter is the initial point from which you started to make, from which you started this traversal. Okay. So I'll tell you, let me just write it. So phi is a map which takes a point, which takes this input point, and which takes a time value, and gives you some point in R3. So what this means is that you choose an initial point P, and you choose the amount of time you want to flow for, and you will get a curve which is phi P at T. Okay. Right, which is basically phi P at T. So phi P at T is, I hope you're understanding this. What is happening is that you are starting off from an initial point P, and you have flowed for time T, and you arrive at a point phi P of T. So now, so it's a function that has two parameters, which is the initial point and the amount of time. So if you fix the time, so if you say that, hey, I'm going to flow for only t units of time and no more. So if you fix time, so let me just write it down. If you fix t, and if you consider this map phi, in which the time parameter is fixed, So I fix the time parameter. So now it is a map from R3 to R3 because the time parameter is fixed. Then this map is basically, then this map is a smooth bijection. It's a diffeomorphism actually. Let me just write it down. This is a theorem. So what does this mean to say that it's a smooth bijection? It means that, of course, it is 1-1, and it is it is uh, it is invertible at the same time. So it's basically, yeah, it is 1-1, and it is also a surjective map. So why is it a 1-1 map? Because let's say you start off from a particular point P, and let's say there's another point Q, and let's say you have flown for some time T and you have flown for some time T, and let's say the two curves have met at a particular point, let's say R. Okay. Now the problem is that the reason why the two flow lines cannot intersect, maybe you've heard this in physics, that if you have these electric field lines or these magnetic field lines, then these electric field lines and magnetic field lines, they never intersect. Okay. You might have asked, why do they never intersect? The reason is that if you reverse the flow, you will get back to the original point. So in other words, if I started off from a point P and flowed from time T and arrived at a point R, then if I reverse the flow, that is, if I start from the point R and flow in for time minus T, which means that I flow in the opposite direction, I will get back to P. This is supposed to be very intuitive, right? Because you have started off from a vector field and you have arrived at R. If you now that if the two integral lines are you will basically end up um, uh, with either P or Q. Okay. And that is why the two flow lines cannot intersect. Because if you flow from if you flow for minus T, that is, you flow in the opposite direction, you cannot necessarily come from 2 points. Okay, you can only come from 1 point, and this basically is a consequence of the uniqueness of solutions of ODEs. Okay, you will only get a unique solution to this system of ODEs. If you have like a system of linear ODEs, if you have a system of first order ODEs, not necessarily linear, you will always find a unique solution. Okay. And so these flow lines never intersect. Okay. And of course, you of course have this. I'm just writing a few things over here. So phi of T plus S is equal to phi of T composed with phi of S. In other words, if you flow for time T plus S, that is equivalent to first flowing for time S and then flowing for time T. Okay. So so essentially you have like a group action of R on the underlying space R3. Which is caused by this vector field. Okay, so I hope this was clear. Now let's come to this problem. Problem is a bit yeah, I mean the problem is a bit tricky in some sense. I mean, the problem is not very clear what the problem asks you to do. So it has given you a surface. Okay. Let me just copy the problem here. So you have a surface over here, but the surface is given by this function. So the surface over here is basically a graph of a function. Okay. Um, in other words, it's a surface which is given by um, a graph of a function. Okay. So just write it over here. Surface. Right. So just think that you have a surface like this. Um, maybe you have like some surface like this, which is where the points are given by x, y, and f of x comma y. So each point on the surface is given by x, y, f of x comma y. Okay. So this is a graph of this function f. Now you have this water which is poured at a particular point. Just for convenience, I'm going to draw like an axis system. So let's say you have a particular point P, where P is 1 comma 1 by 4, where water was poured on the surface. And so let's say there's some water being poured on the surface. And it asks you what path does it flow downhill. Okay.
पेपर के
So of
अंदर
course,
माइनस मार्किंग होगी क्या?
sorry. Hello. Can you ask your question again?
हेलो
Hello. Can you
सर,
ask your
पेपर के अंदर
question?
माइनस मार्किंग होगी क्या?
Sorry. Can you ask again? किसमें? Sorry, I didn't get your question. Maybe you can type that in chat. Okay, just give me one moment. I'll just be back in 1 moment.
सर, अपन पासिंग मार्क्स बता दो कितने हैं? Hello, sir. Sir, I have doubt.
Hello. Yeah. Hello.
सर
Were you
मैं
asking
पूछ रहा हूँ कि
something?
इसमें पेपर के अंदर माइनस मार्किंग भी होगी क्या कल?
I'm not sure. See, I don't. No, I don't think. I don't think there is negative marks. I don't
सर
think so.
इसमें 100 MCQ आएंगे तो उसमें पासिंग कितने के लिए चाहिए?
I don't know all those details. I do not set up the questions. I do not set up the exams.
That
Yeah.
that's why I know. I am not asking questions. I am asking how many numbers are there in passing marks we want to pass the
I
exam.
I don't know. I don't know. That is I don't know that the
Or
exact
in
number.
computer there will be scientific calculator. Or we use scientific calculator in computer.
No, I don't think you can do that. You can't use calculator.
When our result come declare.
The result will come when you take the final exam, right? When you
Sir, it's
take the
our
final
final exam
exam.
only.
Sorry,
Tomorrow is my final exam only.
final exam for this course.
Yeah.
How is the final exam for this course? We're in week 10 only.
Sir, tomorrow my final exam. NPTEL का सर कल फाइनल एग्जाम है.
That's
फिर
not
मेरा तो
possible.
सर वीक
We are
10
in
we are
week
also
10 right now.
yeah we are in week 10 right now but our paper tomorrow NPTEL multi calculus उसका है.
Multivariable calculus.
हाँ
This is not multivariable calculus. This is some other course. This is advanced engineering mathematics.
तो 2 मिनट आपको देख के बता देता हूँ कल किसका है. 2 मिनट रुको बस एक बार आपको. 2 minutes sir only. Two minute only. I log in SWAM.
Okay, let us continue over here. Okay,
सर
so
मल्टीवेरिएबल कैलकुलस का है सर कल.
this is not multivariable calculus.
अच्छा
We
इंजीनियरिंग
are
वाला है. सर इसका क्रेडिट बनी है ना पर
what?
ये कितने क्रेडिट का है कोर्स ये वाला?
I don't know. This is not multivariable calculus.
ओके सर.
Okay. All right. So let us finish this problem. This might be our last problem for today. Okay. So you have this right. So you have this surface which is given by the graph, and there is water falling on it. Okay. Now, if you just sort of think about it, you have this. You have a point and then there's water that is falling on it. Now, you can assume for the sake of this problem that the water is going to flow in the direction in which it's basically going to flow in the steepest direction. Okay. So let me just write it down. So just assume that water flows in the direction of steepest descent. Okay. This is for the sake of this problem. So now we know that if you have a particular function f, then the direction in which the function increases the most is given by grad of f. And the direction in which the function decreases the most is given by the negative of grad of f. Okay. So you're essentially going to move in a direction in which this you're going to move in this direction in which the grad of f value is reduced the most. Okay. So what you want is so you have the gradient vector field, which is defined at each point, which is grad of f. So grad of f is equal to minus twice x minus 4y. So that is grad of f. And I'm in class, okay. Yeah, so you have this gradient vector field, which is minus 2x comma minus 4y. And you're going to flow in a direction which is, of course, going to be parallel to grad f, but it's going to be negative of grad of f. So your vector field, so your integral curve, so let's say x comma t and y comma t are is the curve. Okay, so then your x dash or x dot comma y dot is going to be some scalar multiple of grad of f. Okay, it's going to move in the direction of grad of f, but you don't exactly know what this is. Okay, so what you get is so you get x dot is equal to x dot is equal to minus 2 lambda x, and you get y dot is equal to minus 4 lambda y. Okay, so now you can solve for this. So you get x to be equal to so this is so you get dx upon dt is equal to minus 2 lambda x. So that gives you dx upon x is minus 2 lambda t. So if we integrate this from all right, so you get log of mod x is equal to minus 2 lambda t plus some constant c, which gives you x is equal to some constant c times c1 times e raised to the power minus 2 lambda t. Okay, or in just you can just do like a you can just integrate from um, x equals to 1 to x because the initial point is 1. That gives you dx by x, which is log of x that is equal to minus 2 lambda t. And so that gives you basically x equals to uh, e raised to the power minus 2 lambda t. Similarly, you can solve for y. This is dy upon y is equal to minus 4 lambda dt. You can so that will give us integral 1 by 4 to y dy upon y is equal to integral 0 to t minus 4 lambda dt. So that is so log of 4y is equal to minus 4 lambda t, which gives 4y is equal to e raised to the power minus 4 lambda t. Which is, if you see, this is equal to x squared. And so you get x squared is equal to 4y. Okay. So this is your answer. Yeah, we just solved for the direction in which it will be in some direction of the gradient. Uh, it's going to be in some negative direction. So lambda would turn out to be a negative quantity. Uh, but eventually you just eliminate lambda and t from the equation to get 4y is equal to x squared. Okay, so I hope this was clear. I have more or less covered everything. Yeah, most of the problems are actually quite computational. Um, Okay. Yeah, if you have any questions, you can ask me. Um, we started late, so we are kind of over time today. If you have any questions, you can ask me. I'll wait for some time. Uh, Otherwise, I think I've covered more or less everything that I wanted to cover today. Okay, if you don't have any questions, then I think we're going to stop here.